I'm going to do the test on Tuesday, but on Monday, the last 15 minutes is the non-calculator stuff. Okay? Like I said, we'll talk a little bit more about the non-calculator portion of this stuff tomorrow. Tonight, what we're doing is we're going to be working with graphing and rewriting functions in another style today. Tomorrow, we will go over some of the word problems that are built into this, and it's basically all graphing calculator. So today, we're using the graphing calculator a little bit. Tomorrow, we're using the graphing calculator again, as well as some of the review stuff. And then on Monday, we'll tie up any loose ends that you might have as far as questions and whatnot. Last 15 minutes, we'll take the first part of the test. Tuesday, the whole shebang. Wednesday, we'll start in rationals, which is chapter 9. So, shouldn't be that bad. So, let's take a look at graphing. What I want to do here today, thank you. How's teeth going?
They're not there.
Well, they're doing, I'm assuming that your jaw feels better. All right. So what I want to look at here today is start talking again about how you graph all these polynomials. Now, we've graphed some of these things in the past. What's going to get to become a little bit fancier is that as we raise the degrees of polynomials, some of the complexity of the graphs change.
Is that the example?
Yeah, this is why I'm just starting with something very simple. In this example, we've done this graph before. We've done this. This is a quadratic. And it's written in what type of form? Do you remember what the form is called here?
Extended.
No. Math form. Good try, but wrong. It's called intercept form.
It's not totally wrong. I mean, it's math and it's a form.
This right here is giving you the two terms of the quadratic. Therefore, you'll be able to figure out your zeros. You agree?
Yep.
What are your zeros?
2 and negative 4.
Now, we also know what direction the tails are moving. What direction are the tails moving in this one? They're up. And why are they up? Because it's squared and positive. Everybody okay with that?
Yeah.
We know the tails are going to be up, it's squared, it's positive. So we know it's going to do some sort of a parabola like that. Okay? I don't know where it goes through, I'm not sure about that, but I do know that the tails, with it being a second degree polynomial, this is a second degree polynomial, here's where things start to get a little bit more complex. When you have a second degree polynomial, you will have at least one, or excuse me, at most, one change of direction. You have one change direction.
Having the tails up against it because the first zero was positive?
Not because 0 is positive, because the leading term is positive. If you FOILed it out, you have your A value would be positive. Right? So what I mean here by having one change of direction, whenever you have a squared term, that means you can have up to 2 possible zeros, and also have up to 1 change of direction. You will always have 1 change direction less than your degree. So if you have a 5th degree polynomial, you can have up to 4 changes of direction. 3rd degree, you can have up to 2, and so on and so forth. Does that make a little bit of sense? It doesn't necessarily mean you will always have 1 less, but it means you can have up to 1 less. Yes, sir?
So does that mean, like, could it change 4 times? You always see 3 because 1 is imaginary?
Yes.
Okay.
Yes. That's exactly
Do they
that.
all have, so 5th degree would have 4 terms, but we only see a couple of them.
It's possible. It's possible. You might see all 4 of the changes. It just really depends upon the polynomial.
Okay.
Because we've had 5th degree polynomials that have all real zeros. So we've been able to do that. But we've had 5th degree polynomials that have had 3 real zeros and 2 imaginaries. So it is possible to have that. I mean, we had 1 0 and 4 imaginary. It really depends upon the problem, but it has that basis that you'll have up to that many.
Okay.
Matches the idea of that fundamental theorem of algebra, where if you have, a 4th degree polynomial, you'll have 4 zeros, but depending upon if they're real or not. So it kind of mirrors what we've been doing. Now, one of the things that you're able to do here for certain is that you guys can easily find your y-intercepts. What will always be your value of x at your y-intercept? 0. So if I know my y-intercept is going to occur here, This is one of the things that you would plot on a graph to help give it some, I don't know, maybe some scale, if you will. Because all these graphs are going to look kind of weird, and they're not always going to fit nicely. But if you at least know where your y-intercept is, it's easy to solve for. Because your y-intercept is when x equals 0. So you just put 0 minus 2 times 0 plus 4. What do you get? Negative 8. So my y-intercept is at the ordered pair of 0 and negative 8. Okay. Now, the other thing that we did way back when working with these quadratics is that we worked with the vertices. And if you remember, the vertices on a quadratic were either called a maximum or a minimum. Remember that? What would we have here? A minimum. Now, back when we did that to find that minimum value, you guys did, you'd find the axis of symmetry, substitute it in, get your y values and all that stuff. Big pain in the rumpus, shall we say. Use your calculator. I'm going to show you how to do this with the calculator. Yeah. So what I want to do is I want you guys to get your calculator out, and let's put this function in exactly the way it's written. Parentheses, yes sir?
Can I use the one on the desk?
Yeah, that's fine. So you have, what is it, x?
Yeah, x minus
Minus 2, thank you. And then
x plus 4.
And if you type it in exactly the way that it shows with the parentheses, you don't have to FOIL it, you don't have to simplify any of it. The calculator does it for you. And hit graph. Okay? So as of right now, my rough sketch looks kind of close to it. But I want to find the exact minimum value. In order to find the minimum value using your calculator, if you recall, all you have to do is hit second, calculate, put your feet down. Trace. Not the number 3, but the word trace. Not funny. Are we looking for a maximum or a minimum? Minimum. So you just scroll down or hit number 3. And now you have to do that boundary stuff again. You have to move your cursors either to the left of it and to the right of it. Right now it's to the left of it, hit enter. Move it to the right of it, hit enter, and hit enter again. So it's giving me a minimum value at -1 and -9. Now some of you might be getting some rounding error, where it might be 0.9999 or the -1.0001. It's okay. You kind of have to take, when it's like that, you take it as a grain of salt, it's -1. Okay. What we're going to wind up doing here is we're going to be using our calculators to find these minimum and maximum values. But we're going to be doing it not with just a quadratic. We're going to do it with cubics, quartics, and so on.
There's a word for that?
Fourth degree polynomial is called a quartic.
Oh, I was trying to figure that out the other day, but I couldn't.
After that, I don't know what the fifth one is. What is it?
C-O-R-T-I-C.
Q. I thought it was quart. Yeah, quarts.
I just made that.
Hit enter. Now hit enter again. Now hit enter.
Like a tick.
What you're doing is you're setting a boundary that it's looking for. You're setting it in the calculator. You're putting a boundary here and a boundary here. And it's searching all the x values within that boundary that gives you the smallest value for y. So the calculator's, that's what it does by looking for boundaries.
So do we round up if it,
You'll be able to figure it out. If it's like -0.9999, it's -1. Yes, sir.
Can't we just go into like the table for that one? Because like
Yes.
the boundary stuff never works. Like I set the boundaries and it just says guess.
Okay, well,
-4.
now what happens? I'm just showing you a general way of doing it because now you have a third degree polynomial and you have to do a little bit more work.
All I see is a lot of exclamation points, and I feel like that's every answer to math problem.
Okay.
So,
So,
no big thing I do.
now Clay, I know that you're right. Table functions work great with quadratics. It's very easy. But what happens when you get into the upper level polynomial degrees, you have to, we're searching not for a maximum or a minimum. We're looking for what are called localized maximum and minimums. Let's take a look at this. In this case here, I have function of x is 1/4 times quantity x plus 2 times quantity x minus 1 squared. Now, what we're going to start with, again, is to list out our zeros. We know it's a third degree polynomial, which means it can have up to 2 changes in direction. Start by plotting your zeros. We have a 0 at -2, and a duplicated 0 at +1. What does it mean to be a duplicated 0 at a value?
It changes direction at that point.
It's changing the direction at that point, okay? Now, I don't know if it's changing direction going up at this point, or it could be changing direction going down at this point. I'm not quite sure. But knowing that this is a third degree polynomial because I have x times x squared, if I look at my leading term then, is it positive or negative? It's positive. Now, do you guys remember the trick for finding out the tails? It's like slope. So it being an odd degree with a positive m value then, it's going, so I know that my tails are doing this and coming up. I know that the tails are helping me do that. I don't know how far up that curve is coming or whatever, but I do know since I have a duplicated 0 at 1, it will have to change direction. Miss Colette, you're looking at it all cross-eyed. What's wrong?
I missed the
Okay. When you have a duplicated 0, this is the same thing as saying x minus 1, x minus 1. Do you agree? That's what I mean by duplicated 0. Now, if you graph just that, going the whole, the old-fashioned way of just a quadratic, you'd wind up with that. It touches the x-axis at one spot. That's all it's showing. It's thrown in with another term, therefore it's doing that as well as something else. Okay. So now we're going to do the same thing. We're still going to figure out what our y-intercept is. Your y-intercept is when x is equal to 0, and this should be really easy to do in your head. Your y-intercept would be 1/4, 0 plus 2, and 0 minus 1 quantity squared. So what's 0 minus 1? What's negative 1 squared?
1.
What's 1 times 2? 2. What's 1/4 of 2? 1/2. So my y-intercept then is at 0 and 1/2. Just substituting 0 for x. Now, we're going to put this function in our calculator. People have asked me today, how do you put in fractions? You can do the alpha y equals, or if it's something simple like this is the time I say it's okay to use 0.25 because you're just using your calculator. I think you say
Yeah. How do we, what are we required to have on the graphs?
I'm showing you right now.
Okay.
I'm guessing it's zeros, y-intercept, and what we're doing here. So if you put this in, I'm going to do 0.25 parentheses x plus 2, and then x minus 1 quantity squared, correct? Is that right?
Yeah.
So if I look at my graph, I'm getting that. It mirrors the idea of what we just did with our tails. Everybody see that?
Yeah.
Now, what we want to be able to do is we're going to figure out what these 2 points are. This, move this out of the way, this would be a what's called a local maximum. This would be its local minimum. Because when you're looking at the tails, if you're looking at your tails here, there is no maximum or minimum because they're infinite. It's continuous. They don't change direction after this part here. They're just still going to keep increasing. It's not an asymptote, it's continuous.
That's the one that goes on until it just reaches infinity, but it doesn't reach infinity.
No, the asymptote is when you're approaching something that you never quite get to. This one, you're always going to find another value larger,
Okay.
okay? Or another value smaller,
4 on the floor, so
okay? You don't even know what that references to.
it's like second grade.
What's 4 on the floor reference
No
to?
problems on the floor, like in second grade.
No, that's not what it
Miss Bell
references.
told me.
So you tell your cat.
Oh, okay, so when you feel your cat.
Does any, Olivia would know what 4 on the floor stands for. Text her.
Does that like mean a
No.
Like a
Can't keep
Like
your
a
cows
cow.
on the floor.
Oh,
Is it like a military thing where you're telling him?
Is it a
to
cow
push up,
thing?
like 4 on the floor?
No.
Oh.
Anyway, let me finish this out.
Is it a
So,
cow?
is it a cow thing? That was good. Is it a cow thing? But I want to see if she knows first.
Isn't it with chairs?
No. Originally, 4 on the floor. Now,
Four, like one or four on the floor.
4 on the floor.
Okay.
Now, does everybody agree that that would be a maximum value versus a minimum value? The reason that is because it peaks there and then it valleys here. So in your calculator, you can figure out your localized maximum and minimum by just selecting maximum and minimum. It means the same thing within, all you're doing is with your left and right bounds is you're setting that parameter. You're setting the boundary to look for it, okay? So if I start with my maximum, I'm again picking a left and a right boundary of it, so I move my cursor over to the right of it, excuse me, the left of it, I move it to the other side, and I hit enter. I get a maximum at -1 and 1. They're not always going to be this clean, ladies and gentlemen. It just happens to be dumb luck. A lot of times you're going to get crummy answers with weird decimals, and that's not a big deal.
Yeah, that's what I got.
So it's negative. Okay. Yes, sir.
I googled it.
Well, don't tell anybody until we find out.
I googled it.
That's what they're calling out in school.
You pull up the phone like, ooh,
Write them up.
No, it's okay. Now, do I need to do that? Do I need to use the calculator to figure out my local minimum there for the one where it touches the x-axis? I don't. I don't need to use my calculator here because if you think about it, this was the change of direction.
Right.
That point is the localized minimum. It's where it changes direction. It's at 1, 0. So like Andrew was talking about, what do I have to graph? Well, everything. You're going to plot your zeros, the tails, the y-intercept, and any localized maximums or minimums that may occur. Now, 0? It's at, yeah. Okay. And it doesn't have to be perfect. It's going to be weirdish, and that's okay. All right?
Why can't you tell us? Olivia's not going to do it. Tell CM.
She has the typist right now. It's a little.
Well, let's give her a minute to
It's a
ponder
little
it.
tricky.
She's probably going to Google it. So take a second and do this one. Remember, what most people forget here is when you have x squared minus 9, what are your zeros? Plus or minus 3. It's a difference of squares. So you have zeros at Now I heard you guys say that the -2 gives you a -2 something cubed, x cubed then. So what direction are your tails going? They're going down this way, right? How many change directions can we have up to? 2 of them. So I know it's going to do something like this. I don't know how far up or anything it's going to go. I just know rough sketch-wise it's going to look something like that. We okay on that?
Yeah.
Okay.
Yeah.
Tails, you okay with the tails right?
Yeah, 72.
Oh, wait. All right. Now, when you go to find your y-intercept, you substitute in 0 for x, and what'd you get here?
72.
So at 0 and 72 is your y-intercept. Now you have a local maximum and a local minimum to worry about. What'd you find for your local min?
Oh, God. -3.
What is it? -3 and what? 3 point something?
-3.5 and
3.2? Okay. And then what about your local maximum up here? 0.85. Now, if you look at it, that means my graph is a little bit wrong, isn't it? My curve, my maximum occurred on the other side, so my curve should be a little bit more like that. Yes, sir.
I have a question.
Yes, sir.
So, I was thinking, how do you get the boundaries? Just so like, because you can mess up the boundaries and it doesn't say 3.5, it says like -3.643. How do you get it exactly in the right spot? So it can
You want to be as close to the change of direction as possible. It's just a matter of messing around with it a few times.
Okay, because I'm not good at that.
It just takes time. You don't want your boundary to be so far away a bit closer. Yes, sir.
So like on test, when you want to round it, or
You'll see how these work through a couple of them tonight, and then when I show you answers tomorrow, it's not that bad. It really isn't. Okay. So let me get to the other part of this that I wanted to talk about today, and that talks with how do you write out the cubic function, a cubic function if you're given the sets of ordered pairs. So what's going to happen here is that I'm going to ask you to write out a cubic function. If it's a cubic function, what does that mean the degree is going to be? 3. It's going to be a third-degree polynomial. Now, yesterday when you wrote out some of these things, you FOILed everything out, distributed everything out, and you wrote it out as x cubed plus something and something and so on. When we do it this way, if I'm giving you sets of ordered pairs, we're going to do it just a little bit differently. Yes, sir?
I figured it out.
Okay, we'll worry about it later. Let me get to this. Let me do this first. What we're going to do, we're going to say f of x is going to equal a times 3 sets of things. Now, that value of a is going to allow you to figure out what direction your tails are going, whether it's positive or negative. And I'll show you how we're going to find that here in a minute. Excuse me. If I'm looking at that graph, sometimes they'll give you a graph, sometimes they won't. You can tell me some important parts there. Notice you have 3 zeros. -3, 2, and 5. If -3, 2, and 5 are your zeros, what will those 3 terms become?
X minus 2. X minus 5.
Are we okay with that? Now, we have one other set of ordered pairs there. It just so happened they gave us a y-intercept. Okay. Now, what is f of x synonymous with? Y equals. So I don't have an x and a y? So what you're going to do is you're going to solve for a using 0 and -15. Oops, write that. That fourth ordered pair is not one of the zeros. Do we agree with that?
Yeah.
So what you wind up doing is you use that ordered pair as a set of x and y values to substitute in to find a.
So you're going to X is zeros and Y.
Yep. So -15 will equal a 0 plus 3, 0 minus 2, and 0 minus 1. We're figuring that out. That a value is like, a is like a constant that allows you to figure out, it kind of tells you the compactness or the frequency of how high something, or the amplitude of how high something is going on one of these curves, and how narrow it might be, as well as direction of tails. It's different for each problem, and if you FOIL everything out, then it would just be that leading term. It's basically your leading term coefficient, if you want to think of it that way.
So 3 times -2 times -5
Gives you what? Positive 3. So what is a then? Are you subtracting?
-1/2.
-1/2.
What?
What do you mean what? What's -15 divided by 30?
No. Rewind. All right. How do you get?
Y becomes
How do you?
15, okay.
What's
Not A became negative.
Okay, so is it? Oh.
Do you ever?
I have no idea what you just said, but I'm glad you understand now.
You know the vlog's
I did.
35, 50
3
instead of
plus
50 divided by 30.
-2.
And that's usually what people do.
plus -5, and then they got -4.
So in this, now we have just figured out what the value of a is. So all you have to do is just rewrite out now. once you figure out A is, you have your function of x will equal negative 1/2 x plus 3, x minus 2, x minus 5. And you'll notice that since that first term was negative, remember how our tails were doing that? And that's why it's just showing that's how it was going. That's your answer. You don't have to FOIL it out. You don't have to distribute anything out. When you're dealing with ordered pairs in a polynomial function like this, you're just basically substituting in your zeros and then solving for A and rewriting. It is a lot easier than it looks. Okay?
Well, you just said like it's basically this. Blah, 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 blah,
Okay.
and then you said
What you're doing here is you're figuring out which one of those ordered pairs are your zeros. Once you figure out what your zeros are, you put them into terms. Substitute in that other value of ordered pair that's not a zero, and that allows you to solve for A. Yes, ma'am.
Will we always get a picture of that?
No, and I'm going to do one here in a second to show you what you would do. A lot of times, more often than not, you're just going to be given sets of ordered pairs. And you're going to be told that it's a third-degree polynomial. So I know that I'm going to have a third-degree polynomial. Now, what I would do to start with, especially for the first few of these that I do, is plot them so you get the visual idea of what will it look like. Now, you're not going to know what your tails are doing because you don't know what the A value is. But at least you'll be able to plot to figure out which ones are your zeros if you don't pick up on it. So if you go and plot this one out, you have negative 1 and 0, negative 2 and 0, 0, 0, and 1 and negative 3. So what are my zeros? Negative 1, negative 2, and 0. Are we okay with that? So if negative 1, negative 2, and 0 are my zeros, that means my function of x is going to equal A times x plus 1. And what do I put in the last one? I put x plus 0, or can I just write x? Yeah. You can write x plus 0 if you want. It's not a big deal. I'm just going to write x. I'm going to save lead. Yes. So now what am I going to use? What am I going to do to solve for A? It's the 1 and negative 3. Which one is which? Negative 3 is y. Negative 3 is the f of x because remember, f of x is synonymous with the y equals. If you want to remember that your ordered pairs go x and then f of x, it's the same idea. So we're going to substitute in negative 3 and 1. Okay. 1 plus 1.
2.
3.
Slow down.
11. 21.
I like some puzzles.
Hold on.
Yeah, combine two things.
At this point, it's just a matter of order of ops. You get 1 plus 1 times 1 plus 2 times 1. What do you get?
3.
6. Okay. Negative 3 is 6a. And now what's your A value again? It's not always going to be negative 1 half. Usually people are going to go, is it always negative 1 half? And I say, no, stop talking to me. I'm using one ordered pair that was not a 0. And it just happened to be that. Yes, sir.
Do we distribute the foils to each other first, like add them up to the and then to the end? So we just do 2 times 3 times 1 and then
And then again, when you're done, you just matter of substituting back in your negative 1 half times your zeros. You don't have to, but it's not a bad idea to do that because now you know in this graph. You know now in this graph. Wow, this is really bad. That it's negative, so it's coming up this way. And it's doing that.
Oh, it's doing that.
Okay. And you could theoretically figure out your max and mins off of this. Yes, ma'am.
When you're rewriting the equation for this one, could you put 1/2 x and then x plus 1?
No. Oh, yes. Yes, if you wanted to, that's fine. That's fine. If you want to leave it as just as unsimplified out as just x plus 1, x plus 2, and an x, that's fine as well.
Because I don't like these things.
Okay. And you're done. All right. Let me give you a couple of these shots.
I'd like to solve the puzzle.
That is correct.
What page is that?
Yes, sir.
I actually turned it in one of my notes.
Oh, I did take part. Did you invest it tonight? I can find it.
No, I don't need it.
Okay.